Thank you very much for the invitation, particularly for Professor Zhong to be here. Very nice campus, and I have the honor to present our recent work about how we can use the generative AI for the design and optimizing of the structure. I particularly appreciate Professor Kim that he have already gave a very excellent explanation of what generative AI is. And also, I enjoy AI just now because I don't know Korea, but with the help of AI, I still can know some part of this presentation. So we can see that this is the typical power of AI. So this work is done by me and together with my PhD students here. Okay, so here is the main content of my presentation. So the point one is why we do the work. And point two is because we have many new concepts in my presentation. So I will give a brief introduction about the key concept and technology we are using. And point three, I'm talking about how we can use AI to do the structural design. And point four, we're also calling about how to use the AI to do the structural optimization. And come to point five, we don't only want to publish papers, we also want our technology to go to the real world. So how we developed a platform for there to be used in real world design, and finally come to my conclusion. So first, why we do the work. So currently, we are engineers, and we need to do the design. And most current design currently are based on human labor. So it is very labor intensive. The engineers work very hard, but the design efficiency is not good enough. And this problem is not a problem for one country. You can see that for United States, for China, many countries in the world still have the problem how to improve the efficiency in the construction industry. So if we go further to the design field, we can see that firstly, our efficiency is not good enough to satisfy the demand from the industry. And also we have designed so many buildings, but most of the design results are not being fully reused for guide the future design. And also our design quality are highly reliant on some engineers. If the engineer quit or retired, the design quality will have some new challenge. So we want AI to do the three things. First is to improve the design efficiency. We can make the design quicker. And secondly, we want to make sure that the design knowledge not only stored in the brain of the engineers, but also become a program. The program will become a fixed asset of the design company so that it will be stay there permanently. And finally, we want to use AI to help junior engineers, for example, for our students here, to improve their design quality so that we have a better design in the future. So this is why we do the work. Then we come to the key concept and technology. So today, a lot of people are talking about intelligent. So what is the meaning for the intelligent? So if we go to the Oxford language, we can see that intelligent means that it has the ability to learn. So although we have many, for example, the conventional parametric design method, but all the objective function and the boundary condition are designed by the people. So the program cannot move forward by themselves. So what we want to an intelligent design method means we want the method can learn by itself and keep upgrade itself by them automatically. And then what is generative AI? I think Professor King already gave a good explanation, but I think this animation will show it very clearly. So you can see there's an animation on the screen. The bottom right four faces are the faces generated from the top four faces and left face. So this animation clearly shows the two key points of generative AI. The first key point is that the generative AI, after it learns a lot of data, it can generate a thing that is totally new, for example, a totally new face. The second key point is that the capacity of generative AI is so powerful that it can generate something that almost looks like the real world one. For example, if I don't tell you, you cannot identify these people is the real world people or it is a face generated by the computer. So in 2014, when I first time saw these figures, I think, okay, that will be definitely a revolution in our industry. Why? Because being an engineer, the most important outcome of our work is the design drawing. And in a computer, either you are a photo of a people or a drawing of a building. It's just an image. It's fundamentally the same thing. So if AI can generate a photo of a human looks like a real one, why computer cannot generate a design drawing that looks like the real world engineer's design? So this is the fundamental idea. So if we give enough design knowledge and design drawing to train the AI, is it possible AI can generate a design that looks like a real world human engineer? So then we go further, because there's a lot of algorithms nowadays for the generative design, and we are using 3 key algorithms to generate the design. First, it is called a generative adversary network, GAN. The second one is the graphic neural network, GNN. And the third one is the diffusion model. All the mathematical equations are here, but I think we don't need to talk about this mathematics today. I just give a very fundamental idea what these 3 algorithms did. So the first is generative adversary network. What mechanism is like this figure here. So it have 2 components, the generator and the discriminator. The generator is something like this bad guy. He always tries to generate a new image that is based on the real world image. And the discriminator is like the policeman. He tries to identify this image is a real world one or a one generated by this generator. So if the discriminator identifies this image, then the generator will go back to optimize its parameter to generate a better image. And once the discriminator fails to identify the fake photos, and then the discriminator will go back to optimize its parameter to improve its identification capacity. So they fight at each other, and finally they can generate an image looks like the real one. So this can definitely be used for our new structure design drawing in generation. So we give GNN a lot of real-world drawing, and then the generator and discriminator fight against each other, and finally it can generate a new drawing. The new drawing looks like the real-world drawing. The second one is about graphic neural network. So firstly, it's what meaning for the graph. Graph is a topological structure made with node and edge. It can represent many different relationships, for example, the family, the father, children, mother, anyway. So the GNN is a neural network that can be used to predict the relationship between the graphs. So one of the key algorithms we use here, we call it the age classification problem of GNN. That means it uses age to identify the relationship between 2 objects. So for example, if we see the movie of Lord of the Rings, we can clearly see, okay, this have 4 people here, and these 3 people belong to the wizard side, and that one belongs to the orc side, so we can easily to separate this relationship between different characters. And this algorithm can use, for example, for the layout design of the bins. So we can take each column as a node, and connect all these columns with age. Then we let AI to learn the existing design, then AI will identify some of the age will be real-world bin, and some of age will not bin. So with this age classification algorithm, we can finish the layout of bin. You can see here, the red one is the bin we need, and the blue one is the link we don't need for the real world. And the second algorithm based on GNN is we call it age feature prediction algorithm. That means we still have 2 objects, but we predict some values between these 2 objects. We still use Lord of the Rings as an example, although they all belong to the wizard side, but we can also see there's a loyalty between different characters. So we can also use it for the structure design, for example, for the layout of the shear wall. So between 2 nodes, there are several possibilities to lay out the shear wall. For example, if this shear wall fill with these 2 nodes, then the age feature will be 50%, 50%. But if on the left side it will be wall, and on the right side it will be a door, then the feature of this age will be 50% and 0. If there is a wall on both sides but has a door in the middle, then the feature of this age will be 50%, 50%. So after learning, AI can predict the feature of the edge, then we can finish the layout of the shear wall. And the third algorithm is the diffusion model. Diffusion model is that we can remove the noise from the figure to finally get what we need. So if we have a white paper, it means it also can think about a paper full of noise. And after training, we move the noise one by one, and the color finally left is the drawing we need. Okay, so this is the three key algorithms we are using. And why we need to the optimization? Because first, AI is a probabilistic model. So sometimes AI cannot generate a design good enough. So we need optimization to make it better. And another thing is that AI needs good data to do the training. However, it is very expensive to get a good design drawing for the training. So we can use AI to optimize the training data to get a better design model. And why we call it intelligent optimization is that we don't use the traditional finite element-based optimization method. We use AI, we use big data to do the optimization. And why we can use big data, not the traditional one? That is a good question, and I will expand this question later. Okay, so let's look at how we can do the design drawing. So firstly, we need to get the data for the training. So we take years, we hire engineers, and we set up the biggest training data set in the world. Of course, all these data sets are based on China, but I think that if we have data from different countries, we can also train the corresponding AI model for different country structures. And then we can use AI for the design, for example, the vertical component layout, horizontal component layout, the cross-sectional design of different components, and even some special component like the base isolator. So first, we can look at the vertical component, for example, the layout design of the shear wall. So that is the interesting thing for the research of AI. So once you don't know what to do, you can see how the people do the design, and how do the engineer do the layout design. So this is their fundamental rule. Firstly, the structure engineer gets the design requirement from the architecture. So this is the layout of our room, and this is some design condition, for example, the design intensity. And for the first step, the structure engineer should lay out the shear wall on the place that architecture permitted him to do. And then we consider the design condition. For example, if we have higher seismic design intensity, then we should put more shear wall in this building. And then we do the calculation to make sure that the structure can satisfy the design code requirement. And finally, we bring some empirical rules to improve some details of the shear wall design. So we let AI to entirely follow the human design procedure to generate an AI-based shear wall layout design. For example, for the layout of shear wall, so we need to follow the architectural drawing to lay out the shear wall. So we propose the three algorithms based on GAN, GN, and diffusion model to generate the shear wall layout, and the details are listed on the paper at the bottom of sliders. So here is the result. So on the left are the architectural design of the building, two typical buildings. The gray means the wall, the green means the window, and the blue means the door. So on the right is the layout of the shear wall. So the red lines are the shear wall. So can you identify which one is done by engineer and which one is done by AI? 1, 2, 3. Okay, here is the answer. So you can see that on the top is what we did in 2019, the first result we can get, which is also already very similar to human design. And on the bottom is what we get in 2004. You can see that on the top, there are still some walls with short pier that is not structurally good enough. But on the bottom, the design is almost the same as the human design. So that this is a very exciting result we get to encourage us to do the further study on this topic. And then we need to bring design condition to the design. For example, how we combine the design for seismic design intensity or the height of the building into the shear wall design. So we propose the algorithm to fuse the combine the text and the image to do the learning. And here is the result. So on the left is architectural design. So if you want to design this building on a seismic intensity with 0.1 G and a height of 50 meters, the AI will generate the shear wall design like this one. So if you want to change the height of the building from 50 meters to 100 meters, then several seconds later, AI will generate a shear wall like this one. You can see that with taller building, we have more shear walls and longer shear walls. If you want to change the seismic design intensity from 0.1G to 0.2G, then AI will generate the third design. We can see that because they have larger seismic load, the shear wall will be longer and more shear wall in the design. And then we can bring the mechanics into our shear wall layout. We need to make sure that our shear wall layout can satisfy some design code. So we embedded the mechanism rule into the neutral network. We called it a physics estimator. So the physics estimator to make sure that the building can satisfy the mechanics performance requirement in the design code. And here is the result. We can see that if we don't have this mechanics enhanced design, the totally data-driven design have less shear wall than the human design. That is the design in the middle. But we embedded the mechanics enhanced design into this algorithm. You can see that the shear wall design on the bottom is very similar to the engineered design on the top. And also we can clearly see from the right of the figure is that the AI designed shear wall can clearly satisfy the design code. And finally, we also need to improve some local design to satisfy some empirical rules. So we bring the attention mechanism into the neutral network to improve the local design performance. Here is the design result. You can see that with this attention enhanced design, the shear wall arrangement near to the elevator area is more similar to the human design. And also the structural performance of this result is also similar to the human design. And after finish the layout of shear wall, then we come to layout of the beams. For example, for the frame beams, as I mentioned before, that we can set up the frame beam layout as an edge classification problem. So we have all these columns. We can connect all these columns with edge. And after learning, AI will identify which edge will be the real-world beam and which edge will not be the real-world beam. So we can finish the layout of frame beam. And because the existing graph neutral GNN algorithm cannot learn the rule of the beam layout, so we propose a new algorithm. We called it graph SF. So this algorithm can clearly learn the rule, the knowledge of beam layout from existing design and generate a beam layout very similar to human design. So here is two examples, two real-world frame structure. So on the left is the layout of the column, and on the right are the layout of the frame beam. So can you identify which one is the human design and which one is the AI design? So 1, 2, 3. Okay, here's the result. So we test about 15 real-world frames, and the AI design has already about more than 95% similarity to the human design. And then we move to the layout of the beams for the shear wall. For the layout of beams for shear wall, it will be more challenging than the layout of beams for frame. Why? Because between two columns, it has only one beam. But between two walls, there is a lot of possibility to lay out a beam. So we need to find a new algorithm to solve the layout of the beam. So we propose a method we call the series generated rules to lay out for the beams for the shear wall. And also here is the result. So on the left is the two buildings and with the structural layout. And on the right is the layout of the beams for the shear wall. So the green line means the beams. So can you identify which one is done by human and which one is done by AI? So this is the result. So why we always use this like Turing test to check which is a human can identify which one is done by AI and which is done by engineer? Because we believe that the structural design is a high level intelligent behavior. So it is not easy to simply say, okay, the minimal steel reinforcement or minimal concrete reinforcement use is the best design. So we think that the best way is make the AI design almost as good as this human design. You can not identify which one is done by human or which one by AI. So I think that will make the AI learn more potential knowledge in the engineer's design. And after the layout of the vertical component, then we can horizontal component, then we go to the section design. So when we need to design a section, for example, the thickness of the wall or the diameter of the column, actually this is a compilation of many conditions. For example, the design condition, the horizontal arrangement of this component, and also some empirical rules. For example, we want the column to be symmetric, so it looks more friendly to people. So we propose a rule-embedded generative neural network to generate the section of different components. And here is the result. So on the top is a frame shear wall, and different color represent different section size of the column. So on the left, the AI generates the section design of the column, but the column is not symmetric, so it is not beautiful. But on the right, we embedded the rule, so the AI can generate the column that be symmetric to more easily accepted by the users. And on the bottom, we can see that AI first generates the wall, but the thickness is inconsistent, so it's not convenient to construction. After we embedded the rule inside, all the walls are on the same direction, in the same direction, have the same thickness. And we do a blind test. We use AI to design 71 real-world tall buildings and invited 56 engineers to test. And about half of the AI design are regarded by engineers as a human design. So we can see that the AI design is so similar to the human design. And here is a typical example. So for this tall frame called tube building, the AI design and engineer design, generally they have similar structural performance. And AI design have about 2% less concrete usage, and the human is okay. And if you human do design this tall building, generally it will, even you are very experienced engineer, it take you about 30 minutes to design all these column size, wall thickness of this more than 20-story building. But AI only needs 30 seconds, so it is very, very efficient. And we also can use it for some special component design. For example, for the base isolator, so we combine the discriminator, physics estimator, and rho estimator evaluator together to do the basement isolator design. And here's the result. For this tall building, all these isolator have a diameter of 700 millimeters, and the green ones, the lead rubber bearing, are put outside the building, and the red one, neutral rubber bearing, put inside. So make full use of the torsion resistance of the LRB. And can see that all the key parameters of this structure design can satisfy the design code and not too conservative. And the AI design can efficient design in 30 seconds. It is much, much faster than the human design. And we also can use it for the strengthening design of some existing buildings. For example, we can use it for the BRB strengthening of existing frame. But for this case, the interesting topic is that where to arrange the BRB. Where to arrange the BRB should follow the requirement of the architecture. And the architecture requirement is so complicated that it's not easy to write a explicit rule to follow. So we said, we let AI to do the learning. So we first use AI to learn how to lay out where the possibility location to lay out the BRB, and then we use the optimization algorithm to finally determine the location and the size of the BRB. So here is the general procedure. So it comes to two stages. For the first stage, based on the architectural arrangement, we ask the architecture to generate a lot of training case to say, where is the location you think the architecture can lay out the BRB? And then we let AI to do the learning. So every time you have architecture drawing, AI will generate the possible location to lay out the BRB that can satisfy the requirement of the architecture. And then for the second step, we use the algorithm, optimization algorithm to determine the final location and section of the building. So here is a typical case. So with this building, with the structural layout on the top, firstly, AI will identify the possible position to set up the BRB, and then use the optimization algorithm to know the final location and the section of the BRB. You can see that on the middle, they have a lot of red lines. All these red lines are the location can lay out the BRB. And on the bottom, there is the final location of BRB. So the design procedure takes about 15 minutes. And the most important thing is that this procedure is totally automatic. No human activity involved. AI can directly generate the layout of BRB and also the section of the BRB that can satisfy the design code. And then we come to the intelligent optimization algorithm. Okay, so as I mentioned before, that why we call it intelligent optimization. For example, when we do the optimization, we need to evaluate the structural performance. We need to predict how much material it will be used. So for the both case, we can use the big data to train the AI, and use the AI to predict the structural performance and also predict the structure usage. And furthermore, after the optimization, we don't do it case by case. Every time when we finish optimization of structure, we put this optimization result back to our training database. So this optimized case will be used to train AI to generate a better design in the future. So every time AI do a design and do optimization, they learn something and they can generate a better design in the future. So that is the most important capacity of AI to do the job. Okay, so how we do the evaluation of the structural performance? The key technology we use here, we call it graph representative and GNN algorithm for the different scale information of the building. So if you have a building, you think about what kind of information you have. So you have 3 levels of different scale information. First is the micro scale, means for example, the thickness of the wall, the width or the height of the beam. All this micro level information can be represented by the edge feature of the GNN. And then the middle level information. What is the middle level information? That means, okay, I'll be quicker. the topologic between beam and column, it can be represented by the topologic of this GNN. And you have a macro scale information that we can represent it by the global graph. So we can use it, for example, we first use AI to generate more than 1,000 design results. And then use the 1,000 result to train the GNN to predict the flex spring and shear spring of the multi-degree of freedom model. And we can use the multi-degree of freedom model to predict the installation behavior of the building. So with this result, we can predict the structural performance better than existing model. And the computational speed is more than 100 times faster than the finite element model. So we can also use it to predict the usage of material. In old ways, we calculate the steel consumption component by component. It's very slow. But if you have experienced engineers, you can know how much steel to use with a glance. So we can use a similar way. So we generate more than 4,000 cases, trained the AI, and we embedded some domain knowledge into the AI. So AI can predict the steel consumption very quickly, and also can predict steel consumption in less 1 second. So then if you have a design, we can use the AI-based seismic calculation and AI-based material usage to do the optimization and make it very fast. For example, you have an example here, with just 10 minutes with the GNN-empowered optimization, we can get a design result, satisfying design code. But if we use the traditional finite element-based method, it cannot finish even with 2 hours. And also we can train the design data for the training. So you have a bad design drawing, you will get a bad AI model and get a bad design. But if you optimize the training data, you can have a better model, and have a better AI, and have a good design result. And we do it for more than 300 design drawings, and then we'll have an AI generate result much better with this better training data. And also, we have sometimes kind of data it is unbalanced. For example, in some very high seismic intensity area, we don't have such kind of data. And then we can use AI to firstly generate a lot of data and use the optimization algorithm to optimize the result, and use this optimized result to training AI to get a better design for the special case. Okay, then why we do the work? So we propose, we developed a software called AI Structural Pilot. So it do the local operation on the local computer, and when you finish the AutoCAD, and when you finish the pre-process, you upload the data to our cloud server. The cloud server will use AI to design and send it back to the user. So within 1 minute, we can use 3 different algorithms to generate the shear wall layout, beam layout, section design, and material usage. And they can clearly show at the bottom. And also, you do a click in 3 minutes, we can generate an optimized result that can satisfy the design code, and we can send back the code check result to the users. So here is a typical example. We can see that the 3 different algorithms can generate the design result quite similar to the engineer's design. And go further, we can see that all these design results can satisfy the design code, not only one, for example, inter-storage drift ratio, but can satisfy all these design requirements. And the material usage of this AI design is close to engineer's design, but different algorithms generate different results. So you can pick up which one you interest. So now the platform has been used by more than 100 design institutes and has been designed for more than 1,900 cases by engineers. So when I prepare this slider, I check the database and can say, okay, this is the number 1,914 cases. It is done by this time, and they generate different results. This is an engineer from Shanghai, and this is the design result that can find that it already passed the evaluation design software. So if you're interested in this platform, we have an English version for that. So you can download the software from this website. You can also scan the QR code to access this software. And we also have an English version of demonstrating the use of this software on YouTube. You can go to the YouTube to see how to operate this software. It's totally free now. Okay, so finally, sorry, I delayed a little bit. So I think that the AI is a very important tool to make full use of knowledge and energy. We are using electric to replace human power to do the design, and we can make full use of all these information already designed by the engineers. And with the AI-based generation and AI-based optimization, maybe in someday we can come to a full circle, closed circle with design optimization and learning, and that day will become an emergence of intelligent design. So the AI will become more and more power day by day. Okay, so that's all from the presentation. Thank you very much.